Our next speaker is Erekle Magradze from India State University, and I think this is the only talk about time series, so really excited. Please take it away.
Thanks. So, hello everyone. Thanks for great venue and great conference and invitation. So I will talk about time series forecasting techniques and in general about time series because maybe this topic is not that popular, but I think there are lots of opportunities and gaps that can be filled with the research in this direction, because there are very simple models up to now used for forecasting different types of time series, usually univariate time series, but so if we increase involvement of transformers, for example, or RNNs or CNNs, so modern techniques and in usage of the time series prediction, I think we'll be able to predict for higher horizons, for larger horizons. So right now, like short-term predictions are really good, but long-term predictions suffer a lot with the poor techniques. So my talk will cover so generally it will be general overview of the time series forecasting techniques. Maybe some recommendations how to deal with it, how to start with time series in general, what kind of problems you might face when you are getting the data for analysis. So I will talk about the exploratory data analysis. Also, I will talk about time series decomposition, which is the key approach right now for splitting time series into stationary parts and errors that add some fluctuations to the time series. We'll talk about linear and non-linear models and non-linear approaches. So non-linear approaches, they are so dense in terms of materials that I just mentioned them and gave some links. So whenever you will have time, maybe you will have a look if you're interested in that. And I also have a summary at the end. So time series, right? So it's basically a sequence of data points, observations, measurements. Right now, it's very important to have different types of measurements from IoT devices to control or manage large buildings, large factories, etc., etc. So right now it's very important to analyze this data and have maybe forecast, because you will be able to optimize energy consumption. You will be able to optimize with proper model. So you will be able to provide nice environment for households, visitors to the shops, etc., etc. So it's really important topic right now. And usually time series, of course, they are discrete because we have measurements with some time intervals, but we tend to interpret the time series as a continuous value, right? So we always connect these dots. And what is more important is that time series, they represent the evolution of the dynamic system. So if we have time series for several years for particular, if you are observing a certain system for several years, we might have collected interesting data, and then this time series usually have different characteristics. So with time series, we can also describe, explain, and understand also some malfunctioning and irregularities in the system itself that can help to, that is the basis, for example, for predictive maintenance, predictive analytics, which are the very important and highly valuable topics for the IoT data analysis and machine maintenance and Industry 4.0 area. So what kind of research you can do with the time series? So first of all, you can do correlation mining. Correlation mining is very helpful, and I think one of the oldest topics related to the time series research. So basically, it helps you to identify a relationship between for example, particular customer and another particular customer behavior and another customer behavior, or relationship between the changes in the stock price for one company and its influence in another company's stock price. So basically, you can catch many interesting facts, and also you can understand the trend of certain relationships between two completely independent observations, right? So usually there is also classification or clustering. Clustering is used more frequently because you need some amount of labeled data, labeled time series data, which is very rare for modeling the classes, for identification of the classes of time series. So good example is, for example, geospatial data. If you are observing, for example, growth of the city or the area under observation for several years, you can predict to which direction it can grow. And it's also an interesting topic for planning, also for real estate market. So it helps to identify many interesting interesting features that can be valuable in the future. Outlier and anomaly detection, these are basically the key aspects when we would like to do the predictive maintenance and predictive analytics. So if we are talking about sensors for a complex device, for example, air turbine, or in energy sector, it's really important because maintenance, operations, and fixing huge aggregates that contain lots of components, it's very costly. So if you will be able to, you will be able to detect the anomalies and outliers in advance and have the planned, for example, maintenance period, then the company can save lots of money, and also environment will gain from this a lot. But if there is a kind of emergency outage, then this could cause lots of problems, especially if we are talking about power grids, for example, right? So this is very important topic for in this direction for energy sector in general, for electrical energy, and also not only electrical energy but also for gas pipelines, for example, gas turbines. And of course the forecasting, which is I would say the biggest chunk of the time series analysis process, and it's an area of machine learning, of course. But as I said, there are not that many techniques involved that are used, like really new and efficient techniques that are used in this area. So we are talking a lot about time series. So mathematical formulation is quite straightforward. So if we transform these observations as a realization of some stochastic process, so we will have this set of kind of measurements, right? And the goal for us is to basically find out relationship between the past and the future. And formulation looks like this. So formulation looks like this. So basically here, ET is the series of noises of independently and identically distributed values with zero mean and unit variance. So and ETs are also independent from the past values of xt. And basically, f and g functions, these are conditional mean and variance for xt. And basically, we would like to model f and g in their relationship, roughly to say. And these approaches of the modeling can be categorized as parametric and non-parametric approaches, right? Parametric and non-parametric models. However, non-parametric models can be categorized as and represented as parametric models, but with huge number of parameters, right? So, anyways, we will talk about the parametric models mostly here. And before we start talking about the forecasting, we will talk about exploratory data analysis, which is the crucial part before we start data analysis, time series data analysis in general. So you might face this kind of data. So first of all, you need to do the timestamp normalization, which is important because that helps you to synchronize the data, which is the next step. Then you might deal with this kind of cases where you have lots of missing values and feeling there are multiple strategies, and also this is different area of time series analysis, how you can fill this with these missing values with forward wheel, backward wheel, rolling mean average techniques, and linear or spline interpolation. So you can fill these gaps, and that will help you to model the forecasting, create the forecasting model. If you have multivariate time series where you have dependencies, where you would like to see some dependencies between data, and it's really hard to visualize, so you can definitely use box plots. They are very helpful. They will also help you to identify some outliers, some strange measurements which you can exclude from your analysis. Okay. You can also group time series with certain time intervals, so for certain object, and see how the system has been evolving if you have enough data. And of course, you can visualize data like this to see relationship between different independent variables measurements that you would like to analyze further. So this is the arrivals data, by the way, in 4 different countries. So basically, why we are doing all this, right? So this exploratory data analysis and visualization. So this exploratory data analysis and visualization especially helps us to identify whether the time series is stationary or not. Why it's important to know whether it's stationary or not, right? So stationary time series basically means that it is invariant, its distribution. So its distribution is invariant to time. So you can take intervals so you can take the same time intervals and the measurements done during the same time intervals and check the distribution. And if the distribution is not changing and it fits into the certain range, then you can say that it's strongly or weakly stationary process, which is actually hard to model, but there are approaches that help you to understand this behavior. Also, the non-stationary time series basically shows that you have to maybe it's better, or you have to apply the non-linear approaches for the time series forecasting. So this basically means that the system is growing, evolving in certain direction. So after that you are clear with the time series, whether it's stationary, non-stationary, you can have some feeling after visualization. You have to start with time series decomposition. So time series decomposition means that you have to split the time series in at least 2 major parts, right? Systematic components that basically is not that much changing during the time, and non-systematic components, this is the most interesting part because that's what you would like to predict. So if you will be able to split time series, decompose time series in these 2 parts, where systematic component consists of the average value in series, so trend, seasonality, and also if you will be able to get the noise, then you are good to go with modeling and forecasting the noise only. So more or less, there are many available approaches. So these 2 basically are the most popular ones: the additive model, decomposition. It is based on this rolling mean average approach, and there are also many other approaches, mostly linear. And there is also a multiplicative model decomposition, which you can use. And basically, after decomposition, the time series looks like this. And as you can see here, the residuals are kind of they look weird. So that's the hardest part to model. So if you manage decomposition, then you are good to go with residuals modeling only. And don't try to read this table completely. It's just maybe a good reference to understand how many techniques for the time series decomposition exist, and you can also check the details for each method. There are also methods that helps you to fill the missing values and also decompose the data after that efficiently and take into account this and not lose any data. So I think that will be interesting to review if you're interested in time series modeling. So linear models. Basically, as I said, all you need to do after decomposition is to deal with the residuals, right? And model the residuals that look like this. So basically, modeling again means that we have to find out relationship. We have to find out F and G and relationship between them. ET is again the same kind of component. F and G are conditional mean and conditional variance, but now only for noise. So sorry, for residuals, and that's what we would like to do, right? Basically, if there is a if there is a linear relationship between f and g, and we can model this relationship with linear approaches like the ARIMA models that I will mention later. These models are called linear. So when you just have to approach this with linear combination of certain with linear combination. So that then you can consider that this is the linear model. Otherwise, basically, you are facing with nonlinear models, and you have to apply lots of calculations. Actually, it's very computing expensive. So autoregressive models, it's basically one of the examples of the linear models. Again, we have here hyperparameters basically that we would like to find out this piece, and also this is the set that we would like to search for, and P is basically showing how far we are going in the past. So if we would like to include lots of information from the past, if we have like data time series for several years, then again calculation of these parameters will be very costly. But if we are not going that far in the past, then more or less we can deal with that. But the good thing with this approach is that we can use actually clusterization methods that identify some similar segments. And with these clusterization approaches, we can also identify the length of the P number, basically, right? So, and basically then we're trying to use this information and predict the next values here. So autoregressive models, these are very commonly used linear models, and there are these are basically their kind of incarnations. So SARIMA takes into account also the seasonality information that you can also extract from the time series if you have time series for several years. And basically they are widely used, implemented in many languages, including R, Python. In MATLAB, I think it was implemented like a long time ago. As I said, in case of nonlinear models, there are polynomial autoregressive model, which is very similar to autoregression models in general, but there are some tricks when you have to deal with computations. Functional coefficient autoregressive models, FAR, MSR, STAR, ARC. So these are models that basically differ from each other very much, and each of them has multiple kind of variations. So you can check the details there, because I'm sure I will not be managed to do this in time. And something more, of course. So we have these multilayer percentrons that can be efficiently used also for time series prediction. RNNs can be used, transformers can be used, and also there is approach that can be used also for relationship or rule extraction for the time series. With multilayer perceptron, it's key. The key factor is to arrange data properly. So define how many input values you will have and what will be the output, and this output will be used as an input in the next iterations during the training. And in case of forecasts, you will use the forecasted value to forecast next one, etc., etc. So that's what I mentioned. If you are going far in the future, the error increases, and this is why the long-term forecasting models are suffering a lot. In case of RNNs, basically we have here the process where we have this hidden layer, so X input and Y is the output. And basically, in case of F, usually we are using time on ReLU functions, and we are calculating output with softmax. So again, this has also wide incarnations in terms of combining different approaches, but RNNs show that they are not that good in terms of again long-term predictions. However, there is also one topic that I would like to mention: the evaluation of the model, right, that you have created. So of course you can use root mean squared error, mean squared error, mean absolute error, different metrics, right? But there is a good alternative to the ROC curve for regression models. It's called regression error characteristic model. regression and error characteristic curve. And it's used for regression quality measurement, right? So in case of ROC curves, we are calculating area under the curve. In case of the REC curves, we're calculating the area over the curve. And this is basically the CDF for the error that we're measuring. On the x-axis, we have the kind of error tolerance, so we can define the interval. If the interval equals to 0, we will have, of course, very few number of points which exactly match to the actual values. I mean, forecasted values exactly match to the predicted values, initial values. And if we increase the interval, of course, we'll have higher match. So this is just an example for the SVM. These are basically, this is again the table that will help you to see the techniques for the time series forecasting implemented already, so you can take the ready-to-use packages, libraries, and try to play with them. But as I said, you will see that there are not that many kind of implementations going beyond ARIMA, SARIMA, etc. So that's it. Thank you for your attention.
So, those of us who do not have the background in this area and who started to learn machine learning from deep learning, so there is a generation of us who started deep learning before mathematics, right? So, when we get a time series problem, what we do, we just take some LSTM or whatever and try to predict whatever, both classification, both and also like next step prediction and things like that. So, can you? Does it make sense to compare this deep learning, like stupid approaches, to this more principled approaches? Like, can you? Do you have an intuition when one works, when the other works? Why should students learn this stuff if they know LSTM on PyTorch? So.
Thank you for the question. Actually, the time series time series research is one of the oldest research in data science, as far as I know, because data collection and its analysis is like coming from very old times, since Kepler, I think. Actually, that was the first kind of observations where some interesting discoveries were made, right? So the thing is that right now this area has not that much interest on it, while there is a huge amount of data. So, and when we suffer from lack of data, you can think about time series data, which is available, by the way, in many directions, and the amount of time series data is growing. So, if you just take some LSTM and directly apply to the time series, definitely you will get some result. But if you look deeper and do some kind of time investment, and in learning how to decompose the time series, how to understand whether it's its features, right? Understand similar intervals, cluster this data. So then you will be able to get very interesting patterns in time, and which is crucial in terms of forecasting. And if you are able to forecast something, that's already very good, right? Because we always tend to look in the future, right? So my recommendation is just to invest some time in decomposing time series with very common and plain approaches, and then maybe you will be more efficient in terms of applying deep learning techniques for forecasting.
Have you considered to use ever Holt Winters, the algorithm called Holt Winters, and if yes, what is the conceptual difference between this and, for example, the ARIMA?
Well, basically, they both goes into the direction of the so they both belong to the linear model class. So for the time series modeling, basically, in case of Holt winters, you are extracting more features in terms of season. So you have to calculate basically more parameters in terms of seasonality, trend, etc., etc. So and you have to extract more information from the time series. While in case of ARIMA, it's okay. For example, if you will have to calculate just one set of parameters. So it's slightly modification of ARIMA, but they belong to one class of the linear models. So.
Thank you.
Do we have more questions?
Thank you for the presentation. I have a question about the time series in the financial world. Is there any models that taking into account technical analyses, and there are like chartists who are analyzing the financial data, find some patterns? Is there some models that are trying to combine these two all together?
Yes. So, as I said, the most common approach is to use this kind of linear class models, and that's why I said that there is a huge room for improvement. So what I mean by the huge room of improvement, right? So you can search right now with really nice deep learning techniques the relationship between the textual and numeric data. And the relationship between the textual and numeric data can directly influence many trends, right? Especially in the financial world. Not only in the financial world, but in any other world. So if you will be able to extract the complex relationship between the media, for example, and some trends in financial direction, then that will be, I think, very interesting case of application the deep learning techniques for not only time series, but also the contextual data aggregation and modeling in general. So, as I said, there are not that many papers and publications toward this. So,
thank you.
So thank you for the presentation. I was wondering, do you have any experience and what is your thoughts about using tree models for time series forecasting or explanations? Sharing ideas.
Yes, so there are definitely approaches where you are using this decision trees to model, but first of all, I didn't try them, so I didn't experiment with them. But as far as I know, it's the results, they are not that much better from them, different from these linear models. So maybe this is related to the big amount of data, I don't know. So I don't have right now the answer, but that could be also another direction for looking into it.
Do you know, are there any models, I think that there should be, that do not assume the regular intervals between timestamps and can work with a different distance between subsequent timestamps?
So, for example, there is one approach where you can combine it's a bit exotic technique, so that there is, for example, Fascist Theory, so which allows you to combine the human knowledge and create the inference rules. So you can generate these inference rules and as a human being and as an expert. And also you can apply some machine learning techniques like gradient descent learning, so to generate these rules automatically. And then if you have basically provided time series with different intervals and manage to extract the proper rules, then you will be definitely able to forecast time with different intervals in the future. Also, could be transformers approach that can be used for this kind of mixture, because usually the technique assumes that you have the sequence of data, univariate sequence of data that you are providing as an input, and you have just one output. But if you will be able to provide series or multivariate input data, so vectors, lots of vectors, and you will have also multiple outputs and feed this to deep learning techniques, then you will be able also to predict not the single value, but the sequence of future values. So it should work.
And do you know of any success stories in this field?
Unfortunately not.
Thank you.
Okay.
Okay. Thank you very much, Erekle.